wanted you to be exposed to it, and then a couple of little methods at the end that are really becoming what we consider to be state-of-the-art methods. And if you go into graduate work and you actually do computing, you might either be doing finite elements or a couple of the other methods at the end that I'll show you. The finite element method is based primarily on two techniques. They are integral methods. One is the classical approach is based on the method of Rayleigh-Ritz, or the variational calculus technique. If you go and take a course from civil engineering in finite elements, it will be 99.9% based on structural mechanics, and it will more than likely follow the variational approach. So it's calculus of variations. We tend to do it in the other disciplines, particularly mechanical engineering, with the method of weighted residuals. I'll show you why you want to do that technique. It's much simpler and it works for all equations. This can be limited. But just to give you an idea, in the variation method, you have to have a function that's twice differentiable. You're doing an integral and basically coming up with the equation set that you're going to be solving from the original PDE. If you've ever looked at the Euler-Lagrange equation that comes from calculus of variations, this is the form of the equation that you're solving. That's the unknown, or the equation that would be the PDE that you're trying to set up. You have to establish this functional where anything with an I, that means there's various derivatives, first derivative, second derivative, and so forth. It's a little more mathematically rigorous and can be restrictive with regards to the type of equations, particularly nonlinear equations. The preferred method, and the method that I've used in the books that I've written on finite elements and have taught over the years, is the method of weighted residuals. You don't need a strong mathematical background. You have to be able to integrate. That's about the extent of it. Here's an example. I have an equation, a simple diffusion equation with conditions, the flux condition and a fixed condition. That's known as a Neumann condition in mathematics, and that's known as a Dirichlet. Dirichlet means fixed, and Neumann means a flux. So that's the Q. For those of you that have had heat transfer, that will probably be familiar. This is the range over which the values of X apply. What I want to do is to set up a method of weighted residuals technique to solve that equation. Here's the equation. I'm going to take that equation and I'm going to put it right here. And I'm going to integrate that equation over the particular element that I'm interested in. Now this one happens to be from 0 to L over 2. Don't worry about the limits right now. And I'm going to multiply the equation by a weight. Now that equation, because I'm doing an approximation, it's not actually equal to 0. Why is that? Because you're doing an approximation. And by doing a computer approximation, it's always a residual, like Taylor series. So there's always something that is not exactly equal to the original equation. Does everybody understand? So that means that equation is actually a residual. So I'm going to multiply a weight, I'll tell you what the weights are in a minute, times the residual, and I'm going to set that equal to 0. So what I'm doing is distributing the error throughout the entire computational domain, or the problem domain. The guy who came up with that was Galerkin, and he did it in 1915. He was sitting in a czarist jail. He needed something to do, and he came up with that idea. So 1915, it wasn't until about 1960 that people realized how that could be applied to finite elements. This is what happens. It is not difficult. It looks overbearing here until you see how it works, and then you go, oh, that's not difficult. Here's the equation, so here's the residual times a weight, and I'm going to integrate that. And when I integrate that, then I'm going to say, aha, what I will get will be equal to 0 here. So I'm going to say wherever I have a temperature in here, I'm going to expand this as the product of what we call a shape function, and then the nodal value. The nodal value, that's why you have the t's here with the subscripts. So this is a shape function, and this is the nodal value. So I can say, well, what do I want to use for a shape function down here? And so I'm free to use whatever I would like. I can have linear, quadratic, cubic, any order that I wish. In this case, I'm assuming that I have a linear approximation. So that's what these things do right here. And it says, okay, here's N1, here's N2, N3.
Is that where divergence from variations method is that variations you're not allowed to
No,
have a broader range?
the end result on doing the calculus of variations and the method of weighted residuals is the fact that you get the same equation at the end of the assessment. Then you're free to use whatever element shape you want, whether you did it from calculus of variations or the method of weighted residuals. But you see, in the method of weighted residuals, you can take any equation. It doesn't matter. Take that equation, you integrate it, multiply it by a weight, set it equal to 0. That's all there is to it. Now, the trick to using method of weighted residuals is that you're going to do integration by parts. How many of you remember integration by parts? Remember what you did? Integrate by parts. Now, let me write this down for you because I'm sure in your calculus book you probably had something that looked like this. The integral of u dv is equal to minus uv, or equal to uv minus the integral of v du, right? You had something that probably looked like that. So here's what's happening. That's the equation, right? So you've got the weight in here. So what's going on is that you wind up gaining a derivative in the assessment here, plus this derivative, but this derivative has actually reduced a second order equation to a first order. That's called the weak statement. Weak because mathematically we have reduced from a second order to a first order. It's mathematically legal, but you now have, in essence, an ODE to solve instead of a PDE. Okay, oh, you did? Okay, let's go back. Oops, let's go back. Okay. No, wrong way. How's that? Go one more. There we go. So if I had this technique right here, you see I had a second derivative with respect to t setting there. I substituted the t in terms of the n and t. Remember that expansion, n1, n2, n3? I plug it into there, so now I've got the derivatives with respect to the shape functions. So that has been weakened or reduced, you see, to a first order equation. These are a function of space, so I can solve for those right off the bat. I can do that one time. I can do it up front. I don't have to do it every time. That's what that equation looks like. Now, these little e's right here denote the elements. So if I have two elements, you see what I have, here's the first linear element, here's the second linear element. So that would be E1, E2. So that would be 0, L over 2, and L. So I do the operation on every element. That's why it's a local operation that happens. So all I have to do then is sum what I do per element over all the number of elements. I don't have the constraint, like you do in the last homework, as an ADI method of sweeping in rows and columns, where everything is sequential. I can bounce all over. I can go from this element to that element to whatever I want. So I don't have the problem of having to do things in a sequential manner. That's one of the real beauties of this technique, and the fact that you discretize or you make a mesh of the actual physical domain. It's not something that must be transformed so you can do things in rows and columns like you're doing in the ADI. The reason you're doing that last problem is that that physical domain is rectangular, right? It's easy, so you can automatically do it as sweeps in rows and columns. Those are called structured meshes. In a finite element technique, it's unstructured. It doesn't matter. So this is what the computer is doing when you set this up, and it goes through and it evaluates all these shape functions. That's what these things are right here, all these terms. And so it just does a simple integration. What you wind up with then is, as this thing reduces down, are a bunch of little matrices. That's one of the reasons I wanted you to do matrices at the very beginning, because in the lowest form of finite elements, it gets down to 2 by 2s for linears. So it's a 2 by 2 matrix. And it's easy to solve for all the things you need from the matrix that way. In fact, you can do it with just a couple of lines of code. So this is what's going on. So ultimately, this is what you would get as that particular matrix expression for the first element. So you see we have T1 that would be setting at that node, T2 that would be setting at that node. So if I do this for every element, then all I have to do is just sum up what I've done. So if I do this for the first element, I get this. If I do this for the second element, I would get the same thing again. So how many total nodes do I have? These are called, now, globally, how many nodes? 3. Right? So I'm going to have a 3 by 3 matrix that I have to solve for the unknowns T1, T2, and T3. But I've done what we call assembly. That is, I've done the operation on an element by element technique. And so it makes it very, very quick to do it at that level. So here's what I get for the second element. If I go back, this is what I got for the first element. You notice the global matrix is really a 3 by 3. This is the source term that's setting over here. And then whatever the boundary conditions would be setting here as far as the flux. So you notice here's the first element, nodes 1 and 2. So that's that little 2 by 2 in the 3 by 3. So if I go to the second element, you see here's the little 2 by 2 setting in the 3 by 3. And then what I want to do is assemble them. So I assemble this into the 3 by 3, the global matrix. So here's my global matrix. In this case, it happens to be what? Tridiagonal, right?
So you add them.
So what I'm doing is adding the contribution from the first matrix to the second. And that's where you get into the addition, subtraction, multiplication matrices. That's what you're going to be thinking at in the future when you're starting to do finite element type simulations, probably in your advanced courses as you get into them. It's really matrices, and then how to efficiently solve them. Now you know how to solve matrices. Gauss elimination, LU decomposition, all sorts of things. Right? Skyline method, the Thomas algorithm, all sorts. Now if I put in the boundary conditions, if one of those boundary conditions was fixed, remember T equal T of L, so T at T of L sitting out here would be a fixed value. Remember what it's called? Dirichlet. D-I-R-I-C-H-L-E-T, Dirichlet value. It's fixed. So I can eliminate that. Why would I want to calculate something that's fixed? So that ultimately reduces to just a 2 by 2, of which the unknowns are T1 and T2. So I just plug them into the equation. So here, Dirichlet value, Neumann, and if I happen to have a mixed condition where I've got a flux and something fixed in here, that's called a mixed or Robin condition. So you might run across that, particularly in math, where you say, oh, I've got a situation with convective heat transfer on one of the faces. This would be a mixed boundary condition. Now here we are using, if we go with a quadratic instead of a linear, so we're now going to say, instead of 2 elements, assume that I have only 1 element, and that 1 element consists of 3 nodes. So if I get rid of this, and I get rid of that, and I just have 1 element, I would now have a 3 by 3. So I can write expressions for a quadratic. That's what shows up right here. So it's the same equation that I had. You notice the weak statement. That second derivative has been reduced to 2 derivatives, the first order. And now I just put in the expressions that I would use for a quadratic approximation. And I just plug it into here. And so ultimately I will just solve this as a 3 by 3, just like I did with the 2 elements before. This is what I would get as the coefficient for the 3 by 3. So it looks a little different than what you would get with using 2 elements. What's the advantage that you get in going to a higher order? More accuracy. Now the approximation, doing a linear approximation for something like this with 2 elements is 4th order accurate. If I go to quadratic, it's 6th order accurate. And you can now write finite element codes that are as efficient and quick as a finite difference approximation. So it really behooves you in the long run to get into the method and to understand it. Everybody uses it on the outside in engineering. So that's a generic statement, regardless of what I'm doing. Anytime I see a 1D, one-dimensional finite element, if it's using linear elements, I would have the matrices that you saw before. If I'm using quadratic, that's what it would look like. So it's easy to set up a program that will do that. Now, if we go to 2-dimensional elements, there are really 2 choices of the type of elements that you have. You have triangles and you have quadrilaterals. Here are triangles, here's quads. These things can be fine and do all sorts of things. How many of you have seen pictures like this before? That's the unstructured mesh. That's what they mean by unstructured mesh when you see things like that. You can do it as quadrilaterals as well. The simplest geometry to define an irregular shape is the triangle. That's what Laxmi Gowali was telling you when you had the lecture from him on computational geometry. What he was saying was that given the problem domain, I can tell you what the optimal mesh should be, where the nodes should be placed, what the elements should look like. That's what he does. So if I look at a 2D triangle, it's basically just a triangle with 3 nodes. This is a linear approximation. It's the simplest geometric structure that accommodates irregular surfaces, as I said. You have to remember that since you're doing this element by element, you have what are called the local node numbers, 1, 2, 3, and then you have global node numbers, because you have this, for every element, there's 1, 2, 3, 1, 2, 3. But then you have to associate the local number with ultimately the global number in the whole computational mesh. And it's that global node number that establishes the bandwidth of the matrix. That's why doing computational geometry is important, to minimize the bandwidth. So if I minimize the bandwidth, what does that mean as far as the solution of the matrix? Faster, less storage. If I'm very sloppy about it, I will have a huge bandwidth and it will take forever to calculate this thing. That's why you went through the exercises on matrices and coming up with something better than Gauss elimination. If you want to establish the basis functions or shape functions, the ends for a triangle, it's just a linear approximation in x and y. That's all you do. If you want to do it as a quadratic, you could do that the same. So you already have these computational geometrical relations established for you in finite elements. So you don't have to invent anything new. It's already been around. This is what the polynomials would look like as far as the 3-node triangle. And then ultimately you can solve for those 3 unknowns. You can solve for the area of any triangle. By the way, this is a good little relation in case you ever run across a triangle in which you don't know what the area is. As long as you know these vertices, you can plug into that formula, it will give you the area. The shape functions now for a triangle, you're using N1, N2, and N3. Why? Because it's 3 nodes. Each leg of the triangle consists of 2 nodes, correct? That's a linear leg. So you have 3 linear legs. That's all there is to it. So you now have shape functions for n1, n2, and n3. These are the relations for those shape functions. Here's an example. Find n1 at node 1. Well, x is x of 1 and y is y of 1. I just plug it into that relation. n1 equal to 0 at nodes 2 and 3. Plug into the little relations and what you discover, n1, 0. The sum of all the shape functions, n1, n2, and n3, are always equal to 1. No more, no less. What does that remind you of when we said that before? Remember in polynomials, when we said, oh, the sum of these things can never be greater than 1. They're always equal to 1, the combination. That's the same thing going on here. Point is that you can solve for the shape functions for these various type of elements. If I want to go to quadratic, what do I do? Remember, here's node 1, 2, and 3. All I have to do is add a mid-side node. If I have a mid-side node, I now have a quadratic per leg. 1, 2, 3. So I have 3 legs. So now my matrix per element is 6 by 6, not 3 by 3. What's the relation in going, how many 2 by 2s in a 3 by 3?
4.
A bunch. How many, if I'm going from a 3 by 3 linear element to a 6 by 6 quadratic, how many 3 by 3s in a 6 by 6? A bunch, right? So it's a lot more computational work. So you have to evaluate this. Do I want to use a lot of little linear elements, or do I want to use bigger, higher order elements? That's the big question. How do you solve for these things? You use Gauss quadrature. And for triangles, there's a special set of relations for quadrature that basically you're just going to integrate from -1 to 1. That's basically what's going on. So here's what you get. These are the weights and the Gauss points. That's what comes up here. And so there's a whole table of these things. You can actually put them in a code, and you can say, okay, when I'm doing quadrature, just go and pull the information off the table. You're all done. The other element, quadrilateral. Quadrilateral, four-sided. It doesn't have to be rectangular. It doesn't have to be orthogonal. So it can be skewed, whatever it is. I will transform that into a unit square in computational space because I will be doing an integration by parts and Gauss quadrature where the limits go -1 to 1. So I can take advantage of that and transform x and y into coordinates psi and eta. And so those are going to be orthogonal in computational space. That's fine. It's very simple to set this up. What you wind up with are the shape functions are now defined in terms of these non-dimensional values. And they're easy to solve. So remember, you're doing this element by element. So you do the transformation on the fly. So you do it every element as you go through. So you don't have to do a global transformation to try and make everything look like a box. You only do it element by element. This is what's going on. So if I had that skewed shape before, it transforms into something like this. You notice what the values are for the nodes? They're always -1 or 1. If I do the transformation, this comes from just straight calculus. I'm transforming from xy to psi eta. Anybody know what this 2 by 2 matrix is called? Jacobian. Now, somewhere in your math, might have been in OTEs, I'm not sure, maybe in the 3rd semester calculus, you remember a professor probably saying something about the Jacobian. Well, that's what the Jacobian does. It transforms these things, x and y, into the new variables, psi and eta. So that's what you're doing in the finite element code, is actually calculating the Jacobian per element. Oops, let's go back. If I wanted to go to quadratics instead of linears, this is what I would look for. I now have 8 nodes. Why would I have 8 nodes? 3 per leg, 4 legs. So I have a total of 8 nodes. That's called, by the way, a serendipity element. It's called serendipity because it defines just the boundaries. If I throw a node right in the middle of this thing, then I would have 9 nodes, and those are called Lagrangians. Here's a simple equation. Assume that I've got a conductivity in heat transfer simply constant. Maybe I've got variable conductivity in a material, so I can actually load in the variation in the conductivity that would be setting here and here. This would be the governing equation. That's a Poisson equation. Right? So here is the boundary condition. I'm now dealing with the surface. So it's just different from 1D where I just had this term. Those n's and y's, nx and y, are the normals to the surface because the flux is normal to the surface, so you use sines and cosines in geometry to calculate the normal flux, the direction. That's easy to set up and can be done quickly in a code. Here's the governing equation right here. I multiply by a weight and I integrate, set it equal to 0. That's the method of weighted residuals. That's all it takes. This is what I wind up with. Now, in 1D, it's called integration by parts. When you go to 2 or 3 dimensions, it's called Green-Gauss theorem. So if you want to impress your people over in the math department or somewhere else, just tell them that you had a lecture on application of the Green-Gauss theorem today. It's really integration by parts in 2 or 3 dimensions. That's all you're doing. So here we've established the weak statement. So that second derivative has been reduced to a first derivative. So that's right here. Here, by doing the integration by parts, you notice you pick up the flux boundary condition automatically. That's the beauty of the finite element method. It automatically brings in flux boundary conditions. And if you do nothing on the boundaries, it assumes that every surface is adiabatic, 0 flux. So it's easy for you to go in and add what little values you need for the boundary conditions for this particular technique. So I expand T in terms of the shape function and the nodal values. I just plug this in here. Now by setting the weight equal to the shape function, that's why it's called Galerkin's method. In fact, if I set the weight equal to 1, I would wind up with the finite volume method. And so embedded within finite elements are a number of numerical methods, and it all depends on what you're going to be using for the weights. Anyway, this is what the resulting equation looks like after you've done the method of weighted residuals. You then do the transformation. You're changing x, y to psi, eta. You're using the Jacobian. You can plug in values in here. You see how simple this is to set up as far as a computer code. That should be a 2-2. The final integral expression then looks like this. Now the ij's denote the nodes. So if I'm using a 4-node, what we call bilinear quadrilateral, bilinear because it's linear in each direction, I would have a 4x4. If I'm doing a quadratic, I would have an 8x8. This is what happens if you're going to add convection along a boundary. So the flux is just equal to that convection. So wherever you saw that integral term that was added from the integration by parts, you replace that term with this term. That's the nice thing about finite elements. It's easy to embed mixed boundary conditions into it. This is what it looks like if you were the computer setting up a flux boundary condition on nodes 2 and 3. So if I had an element that looked like this, I would have node 1, node 2, node 3, and node 4. So I would have a boundary condition, a convective boundary condition that would be setting between nodes 2 and 3. How do I know that? Because 1, 2, 3, and 4. So that means that that condition would be setting over here on this boundary. If I go to 3D elements, now that I've got this thing set up and I see what's happening with regard to establishing the equation, it's easy to add just one more dimension. So here's what the 3D equation would look like for temperature, for example. So here's the diffusion terms, source or sink term. This is if there's what we call advection. Maybe there's a wind, or maybe there's a fluid that's moving the temperature around. That's what this is. So this is a mixed equation. What kind of equation is this? You got one of three choices: parabolic, elliptic, or hyperbolic. Let me show you. This is the problem that you will run into when you get to this level of equations. It's elliptic in space. See these second derivatives that are set in here? If these were gone, it would be hyperbolic because they would be first derivatives. But you've got these second derivatives. So it turns out that that's elliptic in space. But you've got this time marching term, the temporal term over here. So it's parabolic as it marches the solution elliptically in space. So it's kind of a combination. So I do the same thing in 3D as I did in 2D or even in 1D. Here's the equation, multiplied by a weight, integrate, set it equal to 0. That's all there is to it. It gets a little more complicated because of the additional terms that you have, but once you set it up, you can see, oh, it's just one more little dimension that I have to do, so it's not difficult to do. Ultimately, you have a matrix that's set up. I don't know what to do with that. It's supposed to be a dot. I think when you see a dot that sets over, it means time derivative. So now the matrix, this is the beauty of finite elements is that you set up matrices, and you only have to do them one time because they're a function of space. Assuming that your elements are fixed in space, you only do it one time, then you're finished. So here's the matrix that would be associated with the time-dependent term. Here's the diffusion coefficients. Here are all the terms on the right-hand side that are given or known. So you can do that easily at one time. So once you've done, then you're free to do whatever you would like with regards to the type of elements that you want to use. Linear, quadratics, cubics, or so forth. Next method. This is called the boundary element method. Now, in the finite element, what I was doing was setting up basically elements that were either triangles or they were quadrilaterals. So you have to create a mesh. In the boundary element method, what do you think happens? All the interior mesh goes away. The only thing you have to do is to set up your node points on the boundary. Whatever the boundary would be, that's all you do. You establish the nodes on the boundary, and you can use what's called the boundary element method to give you the same solution accuracy as you got from the finite element method, but with significantly less computational work. That requires one more method of residuals approach beyond what you did for the finite element. Just one more mathematical catch to it.
That only works if the structure is uniform, correct?
No. Does not have to be structured. It can be irregular. And in fact, with the boundary element method, you can have what are called infinite boundaries. So you have the surface of the Earth, and you want to model airflow through a certain region. What's the upper region going to be? 1,000 meters? 10,000 meters? Outer space? So with a boundary element approach, I can actually have an infinite boundary if I want. That's called the boundary element method, and that evolved about 20 years ago and has begun to replace some of the sophistication and particular applications of finite elements. Now, it does have some limitations, but it's still evolving. So, what happens, you create a mesh on the boundary, whatever the boundary shape would be, and it's easy to go in and find internal values, because if you know what the boundaries are, the boundary values, then you can go in and doing Green-Gauss theorem. You can determine what internal values would be, and you can do this without requiring a mesh. The last method, It's a method I've been involved with now for about 10 years. It's called meshless methods. Absolutely no mesh at all. All we do is just use nodes, and we put the nodes in wherever we would like. Now this is where I get back to work with Shalene as well as Laxmi Gawali, and what's the best place to put the nodes. So we still have to come up with that, but we don't have to worry about discretization, Taylor series, any of that sort of stuff. Triangles, quads, all of that goes away. And so we wind up solving these kinds of problems where we have no grids whatsoever. And it turns out that the accuracy of this method is as good or better than finite elements, or even boundary elements for that matter. So it is an evolving technique that is really now the state of the art, and you're beginning to see a lot of sessions show up in various conferences and so forth. I've had to give panels on this for several years now in the American Society of Mechanical Engineering, and I've got one I've got to do in Florida in the beginning of January on actually applying these methods to some of the engineering problems that we're doing. For example, the indoor air dispersion. We can use a meshless method if we want.
Do you just use a reference point then, that everything's referenced off of?
Every point in here, it corresponds or is tied to the other points in the domain. So you're using a little mathematical trick that says, oh, I don't have to have a connection as I did in a mesh to establish what these values should be. They're called radial basis functions.
They're tied to each other, but nothing external.
All right. Requires neither domain or surface discretization in a meshless method. It's simple in 2D and 3D. It's only a few lines of code versus long subroutines and lengthy code in finite elements, or even in boundary elements for that matter. You can do it with MATLAB. You don't have to do numerical integration. I'm sure that's a relief. There's no Gauss quadrature or any of that that's required. Easy. Easy to code. Cost effective. You don't have to worry about establishing the correct mesh. Is this mesh good? Is it going to give me a converged solution? Absence of a mesh means I can throw points anywhere I want on here, and I will have comparable or better accuracy than I would with a mesh-defined method. Those are the techniques.
So, does it have disadvantages? At what cost?
We at this present time, we are pushing it into nonlinear methods, or into nonlinear equations, let's say. Fluids, heat transfer, things of that sort, where we're trying to get to the same level of sophistication that we've had with finite elements. But if you're interested in pursuing something that's really a cutting-edge technique, meshless is the way to do it. Any other questions? Thursday, we will have a review for the final.